We're changing over to rectangular. It's me again with another video, and this time I'm going to go fast and furious in converting three polar equations to rectangular equations. And keep in mind, if you're watching this video, if you can look at all three of these and you instantly know what type of shape they are, whether they be a parabola or an ellipse or maybe a circle or what's the other one? Hyperbola, ellipse, circle, parabola. Yeah, there's the four, the conic sections. Sometimes these are really kind of fun. If you can't recognize them, then let's just practice, using a little bit of algebra skills and the four equations that we should know that relate polar stuff to rectangular stuff. And I've got them written right up there. So the left side of each equation basically is the polar side, and the right side of each of these four little equations is the rectangular coordinate side. So if you're watching this video, I know this is kind of a little tiny skill. Some universities, play with this a little bit in Calc 3, the calculus of polar equations and so forth. And but in any decent trig class, you should definitely be playing with polar stuff, along with vectors and parametric equations and so forth. So very quickly, trying to keep this really short. This first equation, r times 3 minus 2 times the sine of theta equals 6. I want to get rid of all the r's and thetas, so to speak, and change everything to x and y's. Well, I notice that I've got an r here, and there's an r, and there's an r, and there's an r. I've got the sine of theta, not quite r sine of theta, but we can quickly take care of that by distributing. So this is 3r minus 2r times the sine of theta equals 6, and I can replace r sine of theta with y, and I'll do that very quickly. There you go. Now we got to get rid of that r. And the easiest way to get rid of this r, it isn't to multiply both sides by the cosine of theta or the sine of theta, but maybe if we could get it squared, we could take care of business. So I could go ahead and square both sides now, which would be a horrible idea, because I really don't want to square both sides of this. This is a binomial, and if we square both sides, it would be 3r minus 2y times 3r minus 2y, and then you'd have to use FOIL. So if that's a little confusing, let's take care of that issue quick. What I'm going to do is I'm going to go ahead and add 2y on both sides. Now I'm going to square both sides. So this becomes 3r squared, which is 3r times 3r. This is 2y plus 6 squared, which is 2y plus 6 times 2y plus 6. So this side is now 9r squared, which is awesome, because now I can replace r squared with x squared plus y squared. That's awesome. But let me take care of this side. 2y times 2y is 4y squared. The outer is 12y, the inner is 12y, and the last is 36, which gives us 4y squared plus 24y plus 36. And ultimately, we have 9x squared plus 9y squared when I distribute equals 4y squared plus 24y plus 36. And if you notice, I can now subtract 4y squared on both sides and get 9x squared plus 5y squared equals 24y plus 36. Now at this point, like I said, I subtracted 4y squared on both sides. What I'm going to look at this case right here, where I've got the ax squared plus bx plus cy squared plus dy plus equals 0. I don't have to worry about that xy case that sometimes appears in there. But since these two coefficients have the same sign, but they're different, this is an ellipse. I just looked at the coefficients of the x squared and the y squared. So, cool. Let's play with this one real quick. What I'll do with this one very quickly is try to get it to turn into that one. So if I do that, I just multiply both sides by the denominator. I have r times 1 plus the cosine of theta equals 1. I distribute. This is r plus r times the cosine of theta equals 1. And now I can replace r cosine of theta with x. So I get r plus x equals 1. I could square both sides now, but no, we don't want to do that and get an r squared and r's and make things even more complicated. I'm just going to go ahead and subtract x on each side. Now when I square both sides, this becomes r squared equals 1 minus x quantity squared, which is 1 minus x times 1 minus x. So when I use FOIL very quickly, this is out of the first, 1 times 1, outer minus x, inner minus x, that's minus 2x, negative x times negative x is positive x squared. R squared becomes x squared plus y squared. And if you notice very quickly, my x squares, I can subtract them on both sides, and I'm ultimately left with y squared equals 1 minus 2x. And since there's not an x squared, but only one y squared, one quantity squared, this is the graph of a parabola. Still not a function. You know, it opens sideways, of course. Now, last but not least, let's do the same thing again. So once you work a couple of these problems, they should become very simple. So this is, once again, r times 2 minus the sine of theta equals 8. Let me distribute. This is 2r minus, this is r times 2. R times sine of theta is r sine of theta equals 8. So this is 2r minus r times the sine of theta is simply y. Let me add y on both sides for reasons we've already discussed. And when I square both sides, let's use some of that middle math. 2r squared is 2r times 2r, which is 4r squared. Y plus 8 squared is y plus 8 times y plus 8, which is y squared. 8y plus 8y is 16y. 8 times 8 is 64. Now let's replace the r squared with the x squared plus y squared. And distribute. This is 4x squared plus 4y squared equals y squared plus 16y plus 64. And before we make a determination what of the four conic sections this is, if it is one of them, we'll subtract the y squared on each side, ultimately giving us 4x squared plus 3y squared equals 16y plus 64, which in this case, once again, like the first one over there, is the graph of an ellipse. So you're saying, well, I knew that because both of them were sines, and that was a cosine. Be careful. Sometimes it has more to do with the coefficients that are involved here. I mean, think about it. If I had come down here and subtracted maybe a 10y squared on both sides and got 4x squared minus 6y squared, it would have been the graph of a hyperbola. So be careful making certain, conclusions about just these three that I've worked. But I hope you see the commonalities in all three of them. This is converting polar equations over to rectangular equations, and then identifying what type of graph. Now, there are certain rules to identify what these are without having to do all this work. And if you're at that point, then everything I've done here was pretty simple to you. But I find that a lot of students have difficulty solving equations for a specific variable. And in this case, we use the distributive property, squaring both sides, squaring a binomial, and then knowing these four equations. There's lots of little pieces of math all in here, but it's still pretty fun, and I recommend you practice a lot of these on your own. Till next time. When you're graphing polar equations, we're really just converting them to rectangular.